Welcome. We continue our investigation of the motion of a particle. Next, we're looking at when is the acceleration of the particle 0 meters per second squared? Or probably you'll see that a lot, but my preference is 0 meters per second, indicating the velocity per unit of time. So with that in mind, we have previously found the acceleration function to be 3t squared minus 12t, and the acceleration function to be 6t minus 12. And we want to know when is the acceleration of the particle 0 meters per second squared. So our acceleration function is 6t minus 12. And we want to know when that equals 0. So we can add 12 to both sides of this equation, and we get 6t equals 12, and then divide by 6, and we end up with 2. And so the acceleration of the particle is 0 meters per second when t equals 2 seconds. Now let's take a minute and think about what it means for a particle to be speeding up versus slowing down. And in this context, let's think about movement. Let's think about a vertical number line. And here's where the particle starts. If my velocity, indicating that is the direction I'm moving and how fast I'm moving. If my velocity is in the upward or positive direction and my acceleration is also in the upward or positive direction, then the acceleration is being applied in the direction that I'm already moving. So think about going down the freeway. If I press on the gas pedal to accelerate, I'm going in the same direction of my travel, and we tend to call that speeding up. So when my velocity and my acceleration are both positive, then that is considered speeding up. Now, if we think about this as a freeway here, and I'm headed northward, so my direction of travel is northward, and I'm depressing my accelerator pedal and headed northward, increasing that acceleration, I could alternatively be headed southward on the freeway, and my velocity would still be greater than 0. And if I applied the accelerator pedal while I was traveling this path, then my acceleration, if I press down harder on it, would also, I've got those signs in the wrong direction. My acceleration would be negative just because I'm headed in the southward direction. My velocity would also be negative just because I'm headed in the southward direction. But because I'm headed in the southward direction and the acceleration and the velocity are oriented in the same direction, then I would also call that speeding up. So what this means is that a particle is speeding up when acceleration and velocity have the same sign. So they're both positive or they're both negative. Now let's think about kind of the reverse scenario. Let's say I'm headed northward and my velocity is positive because that's the direction that I'm traveling, But now instead of pressing on the accelerator pedal to increase my velocity, I now press on the brake pedal, and that's going to decrease my velocity, or it's going to have a negative acceleration because I'm decreasing my velocity, or my acceleration is negative. And we do call that process where acceleration, where we press on the brake pedal, we call that deceleration. We're slowing down. We're accelerating in the reverse direction. We call that slowing down. And so we could say the same thing true if I were headed in a southward direction. If my velocity is headed south and I apply the brake pedal trying to reduce that velocity, then my acceleration is negative as well. My acceleration is positive, and because I'm decelerating and pressing on the brake pedal, I'm reversing that forward motion of velocity. And so we also call that slowing down. So what happens is that a particle will be slowing down when acceleration and velocity have opposite signs. So let's go ahead and find out when this particular particle is speeding up or slowing down. So we previously found that our velocity function was equal to 0 when t was equal to 0 and 4. So let's draw a number line here. And here's 0 and here's 4. We also discovered that the velocity function was negative between 0 and 4 and was positive for 4 and above. Now on the bottom side of my number line here, I'm going to insert the acceleration function. And we're going to look where that's equal to 0. And that will help us determine where velocity and acceleration will have either same signs or opposite signs. Now for acceleration, we found that the key point here was 2. That acceleration was equal to 0 at 2 seconds. So what we need to know now is what are the signs of acceleration on either side of 2. So acceleration at t equals 1 is equal to 6 times 1 minus 12. And we can see here that that's going to be a negative number. So from 0 to 2, acceleration is downward. And then we need to test it for values greater than 2. So let's try 10. Acceleration at 10, so 10's way over here. Acceleration at 10 is 6 times 10 minus 12. And this is 60 minus 12, which is clearly positive. So we see that acceleration is going to be positive for values of t greater than 2. So now we look at how these signs for the acceleration and velocity align in terms of their SIGN sign. So on the interval from 0 to 2, we can see that both acceleration and velocity have the same sign, with both being negative. And then on the interval from 4 to infinity, or 4 onward, we can see that velocity and acceleration have the same sign. So we can say that the particle is speeding up on the interval from 0 to 2 union the interval from 4 to infinity. Now, as far as slowing down, we're looking for places where acceleration and velocity have opposite signs. So we see that played out here on the interval from 2 to 4. So we could say that the particle is slowing down on the interval from 2 to 4. So now we're interested in finding the total distance traveled by the particle in 6 seconds. So we're looking at how far the particle traveled from t equals 0 to t equals 6. So let's take a look at what we know about the particle. We know that the particle was stopped, or the velocity equaled 0, when t equaled 0 and 4 seconds. We also know that the velocity was negative on the interval from 0 to 4, and the velocity was positive on the interval from 4 onward. So let's think about what's happening with the particle. So the particle starts, let's say, at this position, and velocity starts out negative. So we know that the particle is headed this direction. Then at t equals 4, the velocity changes from negative to positive. So the direction of travel of the particle changes at 4 seconds and continues onward. And notice there are no other times for which the velocity is equal to 0. So there's no other times where the particle momentarily pauses and changes direction. Now, since we're only interested in the interval from 0 to t, we're just interested in what happens up until, let's say, 6 seconds. So in looking at this, basically what we're interested in terms of how far the particle traveled, is this distance. I'm going to call it d1 for the moment. And this distance from 4 seconds to 6 seconds, call that d2. So the total distance traveled is basically this distance 1 from 0 to 4 seconds plus this distance 2 from 4 seconds to 6 seconds. So to find distance 1, we just need to know the difference in the position of the particle at the 2 times. So distance 1 is going to be, and since this is distance, we're going to go ahead and use absolute value. So it's the absolute value of s of 4 minus s of 0. So the difference between those two positions. Now, due to the direction of travel, this may turn out to be a negative quantity, which is why we've put absolute values around those that difference, so that we end up with a distance which is typically a positive value. And then our distance 2 is going to be similar. We want to know the difference in the position of the particle from t equals 4 seconds up to t equals 6 seconds. So it'll look like s of 6 minus s of 4. And so we can go ahead and compute those. We'll have 4 cubed minus 6 times 4 squared plus 18 minus s of 0, and s of 0 is 0 minus 0 plus 18, so minus 18. And our d2 is going to be s of 6, so 6 cubed minus 6 times 6 squared plus 18 minus s of 4, which was 4 cubed minus 6 times 4 squared plus 18. So simplifying things up a little bit here, 18 minus 18, that will be 0. And so 4 cubed minus 6 times 4 squared, that's going to be the absolute value of negative 32, which is going to give us 32. So D1 is equal to 32 units. Now looking at D2, we have 6 cubed minus 6 times 6 squared. Well, 6 times 6 squared is the same as 6 cubed. So those sum to 0. And so then we have 18 minus 4 cubed minus 6 times 4 squared. Well, the 18 minus 18, those will sum to 0. And then we've got the opposite of what we found up in D1. Notice that this 4 cubed minus 6 times 4 squared is the same as this, which was negative 32. So we're going to have the absolute value of the opposite of negative 32, which is simply 32. So our D2 is equal to 32 as well. So the total distance traveled is 32 plus 32, and of course our units of measure are meters. So the total distance traveled by the particle is 64 meters. I hope this was helpful.